Okay, cool. Let's do stats. So statistics is the science of collecting, analyzing, interpreting, and presenting data. So I did a bunch of statistics last year on my classes and how many people were absent and tardy for each of my classes every single day. I would like to think that my sample, which was a subset of the entire population, my sample helped to lead the giant population of D2 students, the entire membership, to having a new attendance policy. I would love if I was the one that helped make this happen. But I don't think it's just me. There's a lot of people. But also, it's crazy if you have someone with 42 tardies in a class. So that's a lot. So statistics, I looked at how many times people were absent, tardy, right? I analyzed it. I said, what's going on? How's this affecting their grades? Severely? Oh, yes, severely. Because if you're not in class, you're not learning. And I see people fail the exams when they're not here. And I interpreted the results and I said, you know what? You got to be here to learn. I presented the data, sent it to all the people in charge. Cool. And other people did that as well. So it's greatly helped. I want to say this class, there's maybe like two people who are like sick. The rest of the absences have been like field trips or something or sports. And that's it. You guys are like aren't tardy. This is crazy. We're almost 2 months into this semester. And already, this is crazy. You guys are great. You're always here. I don't know. I don't want to give it away. There are people who could beat you single-handedly. It's like this class versus one person. Nope, you guys win. You have less tardies. Measure of central tendency represents the center and middle of the data. So if I look at the number of tardies each of you have to this class, 0. The central measure of tendency is 0. That's the middle of the data. But imagine one of my classes from last year. I had people with 0 tardies. I also had people with 27 into the 30s of tardies, and of course I was 42. That's a lot. So the measure central tendency, it's the center. So we want to see, okay, what's the average? What do most people have? What is it really around? If I want to take the height of this class, roughly, I don't know, what do you say, 5'6"? Is that about the average height here? There's some people taller, some people shorter. I think that's a fair measure of central tendency. The population is the entire membership of objects, people, events, which is to be analyzed, versus the sample is a subset population. So right now in Hebrew class, I believe you guys are doing surveys to ask people about Jag Shack. Does that sound familiar? Yeah, some people are, right. So, but you're not measuring the entire population because I have not been asked my opinion, which I have many. You only have a small sample because you're asking a subset of the entire population. Outliers are values are extremely high or extremely low. So when I look at tests and scores, I look to see if there's any outliers. Did everyone get around to 70% and then one person get 106%? Ooh, that's an outlier. I wonder what happened. Versus, it's an actual average this year for one of my classes for a quiz. Versus, did most people get low 90s on a quiz and then one person get a 50? Ouch, that's an outlier because most are around the same number. The outlier is really far away. It's literally out in the middle of nowhere. Notation. Questions about this, just vocab? I mean, how many of you have heard of this before? 2 people? 3 people? That's it? Okay, cool. If you're going to take stats next year, some of this is similar. If you're not taking stats next year, you can take AP stats. That's also cool. I'm talking about some of the notation. It's just the way we write it. So this first one is sigma. It's a Greek letter. It's literally a capital sigma. You might recognize, okay, so this is the capital. You might recognize the lowercase sigma, right? This is like the mean, the standard deviation. The standard deviation. This means sum. So how many of you guys are in physics or take physics? Couple? Okay. Do you remember learning about forces? Yeah? Do you learn about forces? I look at your face and it's blank. Forces. Okay. So when you sum all your forces in the x direction, you add up all your forces in the x direction, literally your net force. If you're playing tug of war, I could add up all the people tugging and then what's the actual resulting force. The sigma just means sum. It kind of looks like an S. Similarly, if you see like a delta, that's an uppercase and a lowercase, not important, not useful for this class. But this is a sigma. This is how you spell it, S-I-G-M-A, sigma. It's when you take a sum. It kind of looks like an S, right? You sum it up. So X is a variable usually used to represent the individual data values. So each individual data value by itself is going to be represented by X. And then N is the number of data values in a sample versus the capital is in a population. So for example, the lowercase n is the number of people you survey. Number people you survey. Versus n would be the total number of people in the country or whatever. So right now there's this big thing that's going to be happening the end of next month. It's 2020. The last one was in 2010. Does anyone know? Exactly. It's a census. Yeah, every 10 years they take a census. It's mandated in the Constitution. How many people do we have in each congressional district? And then they have to draw new lines. If there's a large population boom, all of a sudden in Wyoming, it goes from 700,000 people to 50 million. Wow, they got to have more representation in the House of Congress. So they reallocate the electoral votes. I mean, there's a certain number of House of Representatives. That number cannot change, so they reallocate, they move them around. So it's very important, if you are a political leader, to make sure the people in your state are counted, right? Because you don't want to lose any representation. Also, there's $1.5 trillion worth of federal funding up for grabs based on population. So very important to fill out the census. And here, we don't want the lowercase n. We want the capital N to fill out the census. We want every single person. And then they send out door knockers if you don't fill it out to try to help the laggers finish their survey and send it in. Fun fact, right now there's this like big hubbub because in 2010 there was a lawsuit because a certain political party sent out a survey that looked just like the census and confused people because they're like, oh, I already filled it out. I don't have to fill out the second one that was the actual census. So there's a law passed, but unfortunately this year, again, they're being sent out. So you are in high school, your parents will fill it out. They'll include you as the number of dependents of living in their household. But this will be the first time I get to fill it out. So I'll bring it in if you want to like look at it. Whenever I get it, I'll bring it in if you want to see. But capital N, that's the number of people who should be taking the survey. Of course, it's not going to be perfect, but the more people, the better. So the mean is also called the arithmetic mean, aka this is what people always ask me. What was the test average, Miss O'Brien? What's the average? Okay, well, this is the exact mean. You add up all the test scores. If I have 5 of them, I add them all up and divide by 5. It's the average. So most people refer to this as the average. It's the measure of center obtained by adding the values and dividing by the total number of values. So if the data was a sample from a population, the mean is denoted as X bar. Just has a bar over it. Literally, so it's called X bar because it has a bar over it. I know, really great, really creative there. Versus if the data are the entire population, we say mu, right? This is going to be the average and we denote it as mu. So most times when we say mean, this is what we're going to be looking for. We're going to be looking for the average in our sample. So the sum of all our data values over the number of data values. So remember, sigma is just sum. You just add them all up. Hopefully that's not new. We're okay? Cool. Oh my gosh, I forgot how much stuff we have to get through today. Yikes. Okay. Less talking about census, more talking about math. Find the mean of the following set of numbers. So to find the mean, right, X bar, I'm going to add up 14 plus 7 plus 5 plus 23 plus 9 plus 1 plus 5 plus 19. I'm going to divide it by what number? Don't say it out loud. Think to yourself, what is our number? How many sets of data do we have? What is it? 8. We have 8 different numbers, and that's our small n because it's just a sample of all set of numbers. So when I divide by 8, my mean is going to be 10.4. So there's some advantages and disadvantages, right? So it's relatively reliable, right? Because it's drawn from samples. Means of samples drawn from the same population don't vary as much as other measures of center. So if I took randomly 5 people from this class, this last test score, take the mean, it's not going to be too different than if I take a different 5 people and take the mean. It's roughly going to be close to the same number. Right? They will vary a little bit, but imagine if I took the mode or the median. Do you remember? Mean, mode, median? What's mode? Yes? Sure. What does mode mean? The most times repeated. What's the median? The one exactly in the middle. Cool. So if I took 5 randomly people and I took the mode, it may not be the same mode, may not be the same median between those 5. So it'll vary a little more. So it takes every piece of data into account. But unfortunately, it's very sensitive, even to an outlier. So it's not a resistant measure of change. Because if I have a bunch of people get 80s on my exam, and then I get one person with a 30, my average is going to be skewed way down. So it's very sensitive. One extreme, one outlier can really affect it. It's not resistant. So if I have numbers 11, maybe 71, 77, 81, and let's make this 83. 91, 94, 97. What do you think the average is about? Huh? Should be around, I don't know, 80s or so is what you think, but it's actually going to be lower because we have an outlier of 11. So it's very sensitive to outliers. So, median, I'm going to use my same numbers from up above. The median is the middle. Median is in the middle of the original data values when they're arranged in order. So they have to be arranged in order, increasing or decreasing. It's literally x tilde. Got a little, if you took Spanish, you see the tilde. X bar is the mean, x tilde is the median. To find the median, first sort the values, arrange them in order, and follow one of these 2 steps. If the number of data values is odd, the median is the number located in the exact middle. If the number of data values is even, it's found by computing the average of the 2 middle numbers. So the numbers I chose before, what was my median? I have 1, 2, 3, 4, 5, 6, 7 numbers, so the exact middle will be 83. That seems like a more fitting measure of central tendency than our mean, because the mean was going to be really impacted by that 11. We're going too fast? We're okay. It's a lot of information. Hopefully you heard about it before. I want you to try example 2. Find the median for the sample of data values used in example 1. So the first thing you have to do is list them in order. So I have a 1, 5, 5, 7, 9. Let's see, 14, 19, 23. So there's still 8 values, so what that means it's an even number, so I have to go to the 2 middle numbers and take the mean of my 2 middle numbers, so that way I have my median. So my median is going to be 8. I want you to try example 3, give number 3 a shot. So write them in order. So it goes 18, 20, 25, 26, and 38. So one exactly in the middle, our median is going to be 25. How do you feel about this so far? Are we okay? Yeah. Sweet. So mean, median, and now mode. So mode is the value that occurs with greatest frequency. So keep in mind, data sets can have one, more than one, or no mode. If you have a bimodal distribution, two data values occur at the same greatest frequency. So this is what happens a lot of times with tests, right? I will have a group over here, and I'll have a group over here, bimodal. Two numbers where it seems like a lot of people are focusing around there. So that's not exactly great, right? A perfect test is in a bell-shaped distribution. So that's what 11.3 talks about, the bell-shaped distribution. So bimodal, two data values occur at the same frequency. Multi, more than two data values occur at the greatest frequency. Or no mode, no data value is repeated. So find the mode of each of the following sets of data. So example A, what is repeated? It's just 1.10. And that's just the mode. That's the only thing that's repeated. What? Oh, there's no tilde or anything. There's no x value that represents it. So here there's two modes. It's literally bimodal. There's two values that occur at the same frequency. Versus this last one, there's no mode because it does not repeat at all. Okay, so now that's how you find measures of central tendency. Like what are most people performing at? What's the average about? Now we can talk about how spread out the data will be. How much variation do we have? So measures of variation tells you how spread out it is. Are you guys okay? You just seem very tired. Okay, see? Exactly. One response, two people looked at me, and one actually smiled, so it's okay. Solid. Hope you, I don't know, had a good day yesterday. You slept a lot, or at least sleep today after school. Oh, shoot. I went hiking, and then I sat down and graded homework for 5 hours, so real great. You missed a lot. Yep. Let's keep going. I'll have the solutions. So the range. So we're talking about how much variance we have. How spread out is it? So the range, the tighter, the smaller the range, the tighter the data will be. So the range is the difference between the maximum and the minimum data value. So you just take the max minus the min. It's very sensitive to extreme values because imagine those test scores I was talking about. If most people were in the 70s and I had one person with a 90, my range is going to be about 20. But really, most people were within a couple percent of each other. So it's very sensitive. It's not as useful as other measures of variation, but it kind of does help us know between which values will we be located. So the test scores for a particular chapter of algebra are listed below. Find the range. So we have to say which one's the min and which one's the max. 97 is the max because it's the largest. 70 is the min because it's the smallest. So our range is going to be max minus min, which is just going to be 27. That's the range. Imagine if my range was 80% for a test. Yikes, what? It's crazy. I would like my range to be small. Ideally, ever in the 90s, plus or minus a couple percent. That'd be nice. Cool. Let's go. Yeah. Okay. So standard deviation. It's a measure of how much values in a set differ than the mean. Okay, so if we have a mean that's the exact middle, and now how far are most data values from the mean? The smaller your mean, the tighter your values, probably the better the test was. So next page is all about standard deviation. So what I want you to do is I want you to read the rest of this page before I go over it. Read through it and I'll explain. All right, are most people done reading? I'm going to summarize now. I just feel like I'm talking too much. Ugh. So, standard deviation. This is, I'm going to teach you how to do it in your calculator after this, but first we're going to do one by hand just for the fun of it because it's not fun at all. So, standard deviation, how much values are away from the mean. So the higher the standard deviation, the more spread out your values will be. It's denoted by a lowercase sigma. So this is a lowercase sigma. Remember, capital sigma is sum, right? This is a capital sigma right here. Lowercase is the mean. So notice that this is each data value versus this with the x bar is going to be your mean. N is your sample size. This is all on the front page of your notes. This was already written for you. So, important pieces of information. It's the variation of all values from the mean. So that means, from the mean means, okay. So if you have an outlier, something that's really far, it's going to screw up your standard deviation. It's going to make it bigger than what it would have. It is 0 only when all the data values are the same number. So what this means is everyone gets the same score. So you all got, 10 out of 10 on your test. Cool. Standard deviation 0 because no one differed from that. This is if everyone has the same score. It's never negative because it's literally a distance. How far away are you from the mean? You could be 2 below, you could be 2 above, you're still 2 away from the mean. It's kind of like if Bradley is the center of our classroom, right? We're all a certain number of steps. Granted, I'm 5 steps away from her on the right side, Jake is 5 steps away from her on the left side, but still 5 steps away. Standard deviation just tells you how far away you are. It's never going to be negative. Larger sigmas indicate more variation. So let's go through a whole example of finding standard deviation. Cool. So all this stuff is tested on SAT. It's also interesting to know data science is one of the biggest booming careers right now. You make good money. You make $130K a year if you have a PhD. Well, it's a lot of money for me. So, okay. General procedure for finding standard dev. You guys didn't look impressed at all. So S here, I'm just going to say is the standard deviation. So there's sigma, there's S. One is the actual standard deviation, the other is for your sample size. I'm going to go through that when I go through the calculator. So specific example, we're going to use 2, 8, 10, 12, and 14. First step, we're going to compute the mean. And then step 2 is do this. So we're going to work our way from inside to out. So first step, compute the mean. To compute the mean, we're going to add up 2, 8, 10, 12, 14, and I'm going to divide by 5 because there's 5 values. So n is 5. This is 14. So you end up with 46, 10, 20, 30, 46 over 5 is 9.2. That's our mean. Now that I have that, see, what's really nice is you could use an Excel sheet. It could calculate most of this for you, or as I'm going to teach you later, you just put all those values into your calculator and it will spit out all the information you need. Cool. So step 2, subtract the mean from each individual value. The result is a list of deviations in the form x minus x bar. So I have 2 minus 9.2. I have 8 minus 9.2. This is a lot of writing, I know. 10 minus 9.2. 12 minus 9.2. 14 minus 9.2. In the background, these are the exact calculations your calculator will do for you. Do you guys need a moment? To write this down, I'll give you a moment. Step 3, square each of the deviations obtained in step 2. So what we're doing is we're working our way from in to out. We started by finding out what our mean was. Then I go through and take each value, subtract by our mean. Then I'm going to square it. Then I'll add all of them up. Like I'm working my way inside to outside. Does that make sense what I'm trying to do? Take the mean. Then I do all these. And then I go through and square it. And then I'm going to add up all the squares. Just working your way inside to out. Okay, so I'm squaring all of these numbers. This is why it can't be negative secretly, because even if you are negative 7.2, if you're below by 7.2, when you square it, it turns positive. So take negative 1.2 squared, 1.44, 0.8 squared, yeah. Yeah, you will. Then add up all the squares obtained in step 3. The result is this top part of the standard deviation equation. So if you add up 51.84 plus 1.44 plus 0.64 plus 7.84 plus 23.04, you will get 84.8. Perfect. Okay, now divide the total from step 4 by the number n minus 1, which is 1 less than the total number of sample values present. Okay, we have 5 data values, right? 2, 8, 10, 12, 14. That's 5 numbers. If 5 is n, what is n minus 1? 4. So I'm going to take 84.8, divide by 4, and I get 21.2. Then find the square root of the value. So square root of 21.2 is going to be 4.6. This is the standard deviation. On average, these numbers are 4.6 away from our mean. Yes, Shane? It is. Yes, because it's a sample. It's the standard of the sample, because sigma is for the whole population. I'm about to go through that in about a minute. Yeah. So SX, because we're going to deal with samples, that's the standard deviation. The sigma is your calculator trying to be smart and being like, oh, if this is just a sample from your whole population, what should the average actually be? That's what it means. Okay, find the standard deviation of these sample values. Do you want to do it one more time, or should I show you how to do it with your calculator? So, calculator. Okay, let's do it. Everyone has your calculator out? No? Lame, come on, calcs out, let's go. Come on. Is that your calculator? Yes? Yeah. Okay, cool. Just try to make sure people don't use other people's calculators. Not nice. Okay, so this whole thing we just did, your calculator does in exactly 2 seconds. let's see what happens. Oops, come on. It's not even opening it. Come on. Okay, wonderful. Come on. Okay, so if I say add list in spreadsheet, or if I'm at home, I go down to where it says list in spreadsheet. So this first line, okay, so I'm going to say 5, 9, 6, 3, and 7. So you're on the home screen, you go to the green where it says list and spreadsheet. The little green, it looks like an Excel file. Are we all there? No? Okay. So it describes right here, using graphing calculators to find standard deviation. In the home screen, open a new spreadsheet, type in data values into column A, and you click menu, statistics, stat calculations, one variable statistics, say okay.
It's not
okay. What?
We can't do this stat calculation.
Why? Wait, what do you mean push OK? At the end? It works.
Let's see the grayed out. So we click
you need to get off of your 7. So you just scroll down, and then now you can go through and do stat calculations. It's because you were in a box.
Okay.
What? There's just one, because we only have one column. Huh? So SX is the way we would calculate it. SX is if we found the mean, this is what it would be. 2.2. So SX is the sample, is the standard deviation of the sample, aka the one we just did. Are we all paying attention? So we just went through this whole thing right here. This is how you find standard deviation, but this is SX because it's for a sample. If I wanted for the whole population, it would be actually sigma. If I plugged in all of my values. Okay. Because we said it was a sample values, the calculator's trying to be smart. It's saying, oh, you only gave me 5 values. I know there's probably going to be like 20 values total. So it's trying to like predict what the actual mean would be. Or the actual standard deviation. All right, let's try it again. So that's 2.2. Let's try it with this one. So you can just do menu, actions, clear all. Hold on. Let's see. Guess not. You can just like X out of here if you want. Do you want to save? No. Go back to here. We're gonna have 2.3, 4.7, 1.6, 7.2, 9.4, 5.1. And you can't leave your cursor on your last number. You have to be off your last number before you push menu, stats, stat calculations, one variable statistics. And which list do you want? Oh, the one we have in A, which is our first column. Cool. And then you can even pick which column you want to put in. So I'm putting in my second column. Cool. So here I find my mean is 2.93. So SX is the one where we would have calculated 2.93. I'm sorry. This is my standard deviation. This is what we're trying to find. The mean is X bar, which is at the top. So the mean is 5.05. Sorry, standard deviation. Standard deviation is 2.93. Technically 2.94. Other questions how we did this one? So I should probably, I don't know, maybe I should make you go through and do that. I showed you how to do it on a calculator. So fun fact, what you can do if you name your list, so I'll just name this list. What I could do then is I could do a distribution table, but I'll do that next time. Here, new table, click to add the variable, my list. Yeah, so it's kind of cool. This is what we're going to go through next time. I just want to show you what your calculator can do. It's pretty cool. So I can change the plot type, so we can have a box plot. This is one thing we're going to learn about as well. I could change it to be a histogram. So no surprise, they all are once repeated. But so we'll do next time. Let me give you out your homework.